Hello, this is Mr. Huber. In this lesson, we're going to look at graphing absolute value functions. Let's first talk about a term called a parent function. A parent function is the basic function that other ones are built from. For instance, when we've looked at linear equations, we've seen y equals mx plus b's. Those are versions of the parent function y equals x. Okay? The parent linear function is y equals x. Then we have, if we change that m and the b, we know that changes the graph some way, just like parents can be changed and look like their relative graphs. Okay? So for absolute value functions, the parent is going to be y equals absolute value of x. And it's a V-shaped graph. You can see an example of one drawn here. A couple things to point out from this. The graph is the same on both sides of what's called the vertex. Okay? The vertex is that point of the V. It's either the lowest point of the graph, or if it was a V that was going down, it would be the highest point on the graph. So the vertex is that highest or lowest point on that V shape. Also, you'll note that you have the point here 2, 2, and then you see on the other side negative 2, 2, right? It's the same on both sides of, in this case, the y-axis, right down the middle of the graph. Okay? And each side of this graph has a slope of 1, or on the left side coming down negative 1. Okay, this part here is a slope of 1, right? You're going up 1 over 1. And on the left side over here, right, you're going down 1 over 1. So the slope is 1 or negative 1, depending on which side you're on. Keep that in mind as we see variations of this parent graph. When we change the parent graph, it's called a transformation. We can transform graphs in lots of different ways. We can change its size, shape, where it's located. We're going to focus on what's called a translation. A translation is when we change the graph by shifting it, moving it left or right, up or down. Left or right would be a horizontal, up or down some vertical change. And again, we've seen that with the slope-intercept form, y equals mx plus b. Right? We change the b value, that moves the graph up or down along the y-axis, for instance. So that's a translation. If we look at a couple of graphs here, we have y equals absolute value of x plus 6. We want to graph it, and then we want to compare it to the parent graph, y equals absolute value of x. So if we're looking at number 1 here, and let's just make a table of values. Okay, let's say we didn't know anything else to do but make a table of values. We'll plug in a couple negative values and a couple positive values. When we plug in negative 2 for the absolute value, we get 2 plus 6 would be 8. When we plug in negative 1 for x, we get the absolute value of negative 1 would be 1 plus 6 would be 7. When we plug a 0 in, we get a y value of 6. When you plug in 1, the absolute value of 1 is still 1 plus 6 would be 7. And when you plug in 2, you'll get a y value of 8. Okay? So we're going to go by 1s on our graph here. Okay? Label our axes, and our scale is going to be by 1s. So if I wanted to graph these points, I'd have negative 2, 8, negative 1, 7, 0, 6, 1, 7, and 2, 8. And you can see then if I drew in this graph, right, I'd have a V shape, like we've seen with the absolute value function. Okay? How does it compare? It is translated or shifted up 6 units. Right? The vertex normally was right here on the parent graph. Right? The parent graph looked like this. And we've taken this whole graph and we've shifted it up 6 units. Okay? Now let's look at number 2. F of x equals absolute value x plus 3, where the plus 3 is inside the absolute value. And keep in mind as well that when you see f of x, that's the same thing as y equals. So we're not going to do much different here other than let's make a table of values. And let's plug in those same x values. When you plug a negative 2 in here, you're going to have absolute value of negative 2 plus 3. That's the absolute value of 1, which is 1. Right, when you plug in negative 1, you do negative 1 plus 3, which is 2, the absolute value, which is 2. Right, you have to add the x value plus 3, then take the absolute value. And you plug in a 0, plus 3 is 3, which absolute value is 3. When you plug in a 1, you get 1 plus 3 is 4, absolute value of 4, and then you'll get a y value of 5. So if I graph these points, I'd have the graph negative 2, comma 1, negative 1, comma 2, 0, comma 3. Let's erase some more of that little line we had there from our other graph. Okay. 0, comma 3, 1, comma 4, and 2, comma 5. We don't see a V here. I wonder why not. Well, it looks like we might have the line going up to the right, but what's happening over to the left? Maybe we need some different negative values. So let's try negative 3, negative 4, negative 5. Let's see if those give us anything different. So if I plug negative 3 in for x, I get negative 3 plus 3 is 0. Absolute value of that is 0. I plug in negative 4 plus 3 is negative 1. The absolute value of that is 1. And I plug in negative 5, I'd get negative 2. I take the absolute value, I get positive 2. So I'd have negative 3, comma 0, negative 4, comma 1, and negative 5, comma 2. So now I can see where maybe I'm getting that left side of the graph shown now. I get my V shape. Okay? My vertex for these two graphs, my vertex for the first graph is right here, right, at 0, comma 6. My vertex for my second graph right here is at negative 3, comma 0. Right. And you can see my graph looks the same on both sides of my vertex going up to the right or to the left. The slope of 1 on the right side, negative 1 on the left side. Right. So we have to be careful when we make a table to make sure we're seeing the whole graph. We're going to see how we can look at the equation and know where that vertex is going to be. And that will help us make sure that we're seeing and we're drawing in the whole graph, not just one side of it or a part of it. Okay. So let's look at quickly how we can describe these graphs and then relate that to understanding how the equation will look for where that translation is taking us in each instance. In this first graph, number 3, we can see that the graph is shifted up to, normally the vertex would be right here at 0, 0. So this is translated up 2 units. Okay. In this number 4, the vertex would normally be here. So you try to think, what would the translation be? Okay, how would we compare it to get it to where it is in the graph we see in number 4? Well, the vertex moved to right here. Right? So it translated right 3 units and down 2 units. Right? It went to the right 3 and down 2. So we want to get both those pieces of the translation in. That can happen. It doesn't just always shift up or down or left or right. In this case, we can see it does both. It shifts to the left or right, in this case to the right 3, and down 2 units. And our vertex here would be at 3, comma, negative 2. Right, a vertex in this one is at 0, comma 2. So you can see that translation right or left, right, is that x value. The translation up or down is the y value. Down 2 units, up 2 units. So let's see how that can relate to the equation and the vertex. After we look at a quick break here to figure out what's so special about the number 2520. It's got a couple of 2's in it, it's an even number, but it's even more special than that. The number 2520 is the smallest number that's divisible by all the integers from 1 to 10. So you can divide 2520 by 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 and get a whole number integer answer. That's the smallest number they can do that. So that is the least common multiple of the integers from 1 through 10. Also, another interesting thing, but maybe not as much so, is if you multiply consecutive numbers, 3, 4, 5, 6, and 7, you'll get 2520. So it's the product of 5 consecutive integers as well. But it's divisible by the numbers 1 through 10, all the integers in there. Pretty interesting. Okay, and it's the smallest number that you can do that with. Let's look back now at our absolute value equations. Okay? We saw where the vertex coordinates would tell us what's going on in terms of our horizontal and vertical shift. Okay? If we look at the equation of a general form, this is like looking at a y equals mx plus b, but we're going to have a y equals absolute value x minus h plus k. H for horizontal shift left and right, and k is the vertical shift up and down. Keep in mind it's an x minus h in there, and so whatever this h value is the x value of our vertex. The k value is our y value of our vertex. So h comma k will give us the vertex. They'll tell us where our graph is shifting, left or right or up or down. Okay? We can see that in this next example. It says, what's the vertex of the graph of y equals absolute value of x plus 3 minus 5? Okay, without even graphing it or making a table, keep in mind this is x minus h plus k. Okay, so that's x minus negative 3 plus negative 5. So there's our h value, negative 3, our y value, negative 5, k value. So it's our x and y of our vertex, negative 3 comma negative 5. This graph would be translated left 3 units and down 5 units. Okay. Because of the h value here, again, it's a minus h, so we always go with the opposite sign of what you see there. So the h value is a negative 3, the k value is a negative 5. Negative 3 comma negative 5, that would be the vertex. We can use that then to draw our graphs more simply. Okay. If we look at a couple examples here, if I want to graph y equals absolute value of x minus 1 plus 4, I'm not going to make a table of values. I'm going to identify where is my vertex. My vertex is going to be at 1 comma 4. Right? I'd have x minus h plus k. H, k. So I'll go by ones on my graph here. If I go to 1 comma 4, that'd be my vertex. And then I just have a slope of 1 for the right side of my v and negative 1 for the left side of my v. And there's my graph. If you want to test it, let's check this point right here. Right, that'd be an x value of 3. So let's plug a 3 in. We'd have y equals 3 minus 1 plus 4. That'd be y equals 2 plus 4. The absolute value of 2 is 2 plus 4, that'd be 6. So I should have the point 3, excuse me, comma 6, not 2. Okay, so I should have the point 3 comma 6. Right? I plugged in a 3, I got out a 6. This, in fact, is the point 3 comma 6. It would work for any of the points. Again, we find the vertex, then we can just draw in both sides of that v. All right? If we look at number 6 here, okay, keep in mind, right, this is x minus negative 5 plus negative 8. Right? Our h value is negative 5. The opposite of the sign we see here. It's x plus 5, our h value is negative 5. Over here we saw x minus 1, our h value is a positive 1. Right? So we have negative 5, and then our k value is negative 8. So we have negative 5 comma negative 8 as our vertex. So I go to negative 5, negative 8, right there, and then I draw in my graph. With a slope of 1 and negative 1 on each of those arms of the v. Negative 5 comma negative 8. And we saw in this graph here, the first one, again, our vertex is at 1 comma 4, 1 comma 4. So identify the vertex, okay? Number 5 is shifted to the right 1 and up 4. Number 6 is shifted to the left 5 and down 8. We find that vertex and then just draw in the rest of that V-shaped absolute value graph. Now you've had a chance to see some examples. Maybe go back, replay, and try some on your own if you needed to do that again. And you can test yourself out by taking the absolute value functions quiz that's posted on Moodle. Good luck.